All right, Curtis, you want to share your screen?
Yeah, I'll share here. Did it come up there?
We see it here.
Okay. So, sorry, I'm not there. I was asked to talk about, try to explain what spin density matrix elements are, because we've talking about measuring them as one of the early parts of the program, and so sort of go through. I'll start by saying a little bit about the spin density matrix for a photon, basically how you measure the category or describe the polarization, then photoproduction of vector mesons, and then these SDMEs, the spin density matrix elements, as observables, and then connected to the decay of vector mesons. And then I'll tie these into other polarization observables whose names may be somewhat more familiar to people. They're basically another way of looking at that. And then talk about a method that we developed. Mike Williams was here on how to measure spin density matrix elements in a way that retains a lot of the correlations and relationships between different ones that's lost if you do sort of a standard way, and then a summary. So start with the photon density matrix. So that it's basically an alternate way of expressing the polarization of non-zero spin objects, so spin one vector or photons. And it can be used to represent a pure or a mixed state of polarization. So, and that's the nice thing for us, is because our photon beam is a mixed state. There's some fraction that's linear and there's some fraction that's unpolarized. We just start with the two helicity states in circular polarization, the plus and the minus. You think of right-handed and left-handed. And you could talk about the photon basically being a combination of the right-handed and the left-handed state. The density matrix is sort of this inner product of the two photon wave functions, or the states, and it's represented by this 2x2 matrix. And nominally this would be a 3x3 matrix for a spin 1, but you can't populate the m equals 0 state of a photon, so it's basically suppressed. So there's the two states here, the plus and minus helicity states. So that's the general representation there. It's a Hermitian matrix. It has a trace of 1, so that basically is a probability constraint. And if you look at the right-handed and left-handed circular polarizations, the density matrices are just these simple single elements in here, the one state and the two helicity states, the plus 1 and the minus 1. And those are pure states. You can take a circularly polarized beam where you have some fraction of circular polarization that's less than 1. So there's some p, which is that fraction, and then there's the helicity operator, which is the plus 1 or the minus 1, and you define this eta, which is sort of the folds in the helicity and the degree of circular polarization. And the density matrix goes to this quantity down here, this 1/2 times 1 plus the eta c, 1 minus the eta c on the diagonal. So if eta c is plus 1, then you're going to get a 2 up here, a 0 down here, and you return the right-handed state. If it's minus 1, you're going to get a 0 up here, and a 2 down here, so you're going to return the left-handed state, and it basically encompasses any possible combination. So that's circular polarization. Linear polarization states can also be built out of these two helicity states. There is a complex exponential, a rotation, and so this alpha is the angle between the polarization vector and the production plane. And the general pure linear polarization states are expressed by this matrix here, the 1/2 for the trace, and then the e to the minus 2i alpha and e to the 2i alpha here. So that's the general linear polarization. It's an off diagonal, and the alpha basically, for our case, is the, if you will, the para or the perp. And you can express this as a sort of a vector here. So the linear polarization, there's a cosine 2 alpha and a sine 2 alpha. So the first and second elements of this vector, and they feed into this, so that's the cosine 2 alpha or sine 2 alpha that come out. And then the circular polarization can be added in as just the third element, which is plus or minus 1. And again, if you have partially polarized linear polarization, which we do in the experiment, then there is the polarization degree of the photon, which is something 30 to 40% for us, and then this e to the 2I alpha, or 2 e to the minus 2I alpha. So this is the density matrix here. That just describes the initial photon state that we have, and knowing the polarization lets us write that for each one of our events. Okay, so what do you do with that? That density matrix, coupled with the production amplitudes T, so there's a production amplitude T, it's T dagger, the density matrix of the initial photon, gives you the density matrix of the produced vector meson. So the production mechanism, coupled with the initial state of the photon, gives you a density matrix of the vector meson. And in the same way, this density matrix of the vector meson characterizes the polarization of that produced vector meson. And these amplitudes here are a function of production angles and energy and so forth. So this is not just a number, but it depends on, if you will, the angle of the produced vector meson, the energy of the beam, and so forth. So it's something that has to be mapped out. And if you have these amplitudes, so these can come from some theory. So this is how our theorist friends would connect in with the density matrix. They would, our photon beam is here, their amplitude describing production is here, and that gives a prediction for the spin density matrix elements. And so they characterize these. It's basically a sum over all the helicities of here's the vector meson, the outgoing, outgoing nucleon, I guess there's an extra lambda floating around in there, sorry. This is the photon, and then the target nucleon. Here's the photon density matrix, and then the complex conjugate. There's some normalization factor. So the density matrix of the vector meson, these elements here, which is a 3 by 3, is basically this sum over these theoretical amplitudes, or however you got them, the density matrix of the initial photon beam. And with photons, a common thing is to decompose this density matrix into basically 4 components that have to do with the polarization of the photon. So 0 component is unpolarized, that's the row 0. 1 and 2 go back to that density matrix of the photon, the cosine alpha and sine alpha, they're linear polarized, and then circularly polarized is 3. And so it decomposes into this sort of sum here. So there, the total density matrix is the thing you could measure with unpolarized photon beams, because the vector meson is self-analyzing, and then things that require either linear or circularly or some combination thereof polarized beams that decompose this.
Hey Curtis, what does self-analyzing mean?
So because the particle is spin, and you measure it, the decay distribution is not going to be isotropic. So the angular distribution of the decay particles of the vector meson are coupled back to the polarization of that. And in this case, it's coupled back to these spin density matrix elements. So because there is a polarized vector meson that's produced, it's not an isotropic decay, and so you can learn something about that polarization from the decay of that. So you don't need a polarized beam to produce a polarized vector meson. So you learn something there. Is that okay? And these rows can be basically extracted out from these production amplitudes. They're these sort of sums here, the row 0, row 1, row 2, and row 3. And it turns out there's a bunch of symmetry relations between the amplitudes and the spin density matrix elements, and there are only a certain small number of real unique elements here, and so everything I've written down here is real. So the row 0, 0, 0, 0 is real, this one is real, this is purely real, it's an off diagonal, so I wrote it as the real part of it, but there's no imaginary, there is an imaginary part, so there's a real and imaginary part of this one. And same for the row 1, they can be projected out from these amplitudes, and it basically has to do with putting the correct density matrix for the photon in, calculating it. So there's 5 things here that in principle exist. Row 2, there's 4. Row 3, there's 4. And if you look at these, there's some interesting symmetries between them. The 0 and the 1 are symmetric, and they basically, there's a flip in the photon helicity here. So you got a this couples the same helicity here, and this one couples opposite helicities. And then if you go down to the 2 and 3, there's a similarity here between them. There's I in front of them. Now, it turns out if you measure things, you can only measure some subset of these. You can measure 3 of the row zeros, 4 of the row 1s, 2 of the row 2s, and 2 of the row 3s. And I'm not going to go into that. But that you need, basically, my understanding is you need things like dilepton decays of these to get access to the other ones. But for simple pseudoscalar decays of these vector mesons, this is what's measurable. And so you have these massive looking things here written out of all these elements, the row 0, the row 1, 2, and 3, and I wrote them out there. That's not critical. Once you have that spin density matrix, there is a decay amplitude for the vector meson, which is probably something we know. We know how vector mesons decay into pairs of pseudoscalars or 3 pseudoscalars. So there's some amplitude m we can write down. And that then gives us an angular distribution, which is related to a differential cross-section that we measure in the lab. So if we know the spin density matrix of a vector meson and we know how it decays, you can predict a decay angular distribution. The other way is if you know the decay angular distribution, you can get back to the spin density matrix element. So this is how one goes about measuring these spin density matrix elements as an observable. And this basically expands as this sort of thing here, where these are just various D functions, which are sort of generalized YLMs, which is good enough for right now, and various directions. So the row decay, we've been talking about basically the decay of one of the pi's being one of the directions, and if it's an omega, it's the normal to the decay plane that define these directions. But this is sort of the thing, how we'd go about measuring these. And this is what I think Mike Steibel to talk about how we would actually measure these in the experiment. Turns out this is if you write this out, these are the sort of angular distributions that you look at to measure. And so if you measure these distributions of the decay, then you get at the row 0, and if you have linear polarized, the row 1 and row 2, and sort of fitting these angular distributions lets you pull back out these elements here. So that's sort of what Mike will tell us how we'll do in our data. This is probably the way we'll start out measuring these. So what are these exactly? So if we go back to pseudoscalar meson photoproduction, and things defined in the center of mass, there's a bunch of observables that we're familiar with for unpolarized beam, and there is just a differential cross-section, single polarization, there is a recoil nucleon polarization, which is P. There's this sigma, which is a linearly polarized photon beam, so it's an asymmetry there. And there's a target nucleon asymmetry as well between the two states there. So those are the single nucleon observables for pseudoscalar meson photoproduction. And then there's a number of doubles, so if you've got 2 polarizations. So if you have a polarized beam and a polarized target, there are a couple that you can do with circularly polarized depending on the polarization of the target direction. There's also a couple for linear polarization. And then there are beam recoil. This is a transfer of polarization from the beam to the recoil nucleon. With circular, they're known as CX and CZ, and linear, they're known as OX and OZ. And then there's target transfer to the recoil again, and there's these here. So these are things you often see if you're looking at or watching talks about baryon spectroscopy. These observables are a lot of things that are fit to. Do the same sort of thing with vector mesons. They're a little more there because the vector meson spin 1 is self-analyzing. You automatically get single spin observables just by producing it. There's the differential cross-section again. There is a vector meson polarization, there is a beam asymmetry. This is what we've been talking about. There is a recoil nucleon polarization, target asymmetry, and then there are something called a tensor meson for the vector meson. These are basically the same thing that we would see before. The tensor is because it's a spin 1. It's a matrix. It's not just a simple polarization. It's a little more complicated. And these quantities here relate to the spin density matrix elements. And they basically, the tensor here relates to the rho 0, 0, rho 0, 1, 0. And these were all measurable. And then the vector polarization is related to the one that we can't measure. So you can't actually access the vector polarization, but you're basically measuring with the rho 0 the tensor polarization of the omega or the rho meson that's produced. So that's the physical meaning of this. They're a tensor polarization. When you add linear polarization, there are there's double spin observables, there's still the beam asymmetry, there's these C's again where you transfer polarization, the photon polarization to the vector polarization or to the tensor polarization, and there's two different degrees of linear polarization. There's X and Y, they correspond to 1 and 2, but it's basically transfer of the photon polarization to either the vector or tensor polarization of the meson. And so that's what generalizes here for linear polarization, that transfer. Okay. And these, again, are related to spin density matrix elements. They now come in being the rho 1s and the rho 2s here. Here's this beam asymmetry. It's the rho 1, 0, 0 plus 2 rho 1, 1, 1. And I'm going to go back very quickly to this horrible slide with all these matrix elements here. You see this messy slide? It's this here. The sigma is basically the trace of the rho 1. It's twice rho 1, 1, 1. There's two of those in the rho 1, 0, 0. So that's what the sigma corresponds to. It's the trace of this rho 1 spin density matrix element. Now, okay. And so, again, you can see what could be measured it's the transfer of the linear polarization to the tensor polarization. See that here, but we can't get the transfer to the vector polarization. So we really can't access the vector polarization, but the tensor polarization and the spin transfer there. So that's if that's an easy way to understand what these means, that's what they're coupled to. They're basically related to other observables. It's just a different language to write those in. The spin observables that we can measure. Now, you could also say, well, another way to do this, if we could accurately describe these production amplitudes, but by fitting something in our data to produce these, then we could project the spin density matrix elements out of those. And this method then would retain all the correct correlations between elements of the spin density matrix elements. Nothing would be outside of its physical range. They'd all be constrained by everything we knew in the experiment. And so this was something that we tried to do, and how we extract them. It's in class with the procedure developed at CMU. The idea being that we try to construct the entire amplitude. So you produce the photoproduction, you have a vector meson intermediate state, and then that decays. And we wrote this, basically we said, well, we don't know what this amplitude is, but we can make if you will, a Taylor series expansion in terms of S-channel waves. So we put in S-channel baryon waves. That happened to be what we were working in class. And so you'd basically sum over the waves from spin 1/2 up to some high number, 15 halves or something. You'd look at both parity. And you'd write, and the amplitude would be some sum of these that depended on the experimental weights and a set of complex weights that described each one of these, how much they went in. And by fitting this amplitude that you create here can describe your data very, very well, but it probably doesn't have any physical meaning. But it is a model of the total amplitude, and it's an accurate model of the total amplitude. It's got all the correlations in it and the complex pieces. So you could use this model to project out the spin density matrix elements. And that's sort of the trick that we did. So you use this complete set of S-channel amplitudes described here. You basically use that to produce an intensity, which is then compared to the experimental data, so a log likelihood fit event by event. And once you've got this, then you can produce the cross-section. And if you back off and don't compute the decays, you can extract out the spin density matrix as well. And this method is also nice because it describes the data in all the dimensions with this amplitude that really has no physical meaning other than it describes the data. But because it describes the data, you can project out observables. And it handles both linear and circularly polarized and unpolarized photons. And the other nice thing about this method was it also builds in detector acceptance. So if your Monte Carlo is very good, you can basically generate a set of raw data that is uniformly populating phase space. You run that set through your Monte Carlo and you have an accepted data set. So you have a raw and accepted. And because you have a physics model now that describes your data, that physics model is the thing that is always messing you up when you're trying to compute an acceptance. You need to know what the underlying physics is. It comes out of this from this model. You can now actually use this to compute an acceptance here without having to have a theoretical model for this. So at some point we will have a good enough simulation that we can actually model free compute the acceptance of the detector here. So that's the nice thing here. And then these are some preliminary class results on a couple of these spin density matrix elements. If you go back to what Volker showed on Monday of this week, so on this plot here, I have the row 0, 0, 0 and the row 1, 0, 0 elements. The 0, 0's in black. Black ones are published. The blue ones are the row 1s. And there's some interesting features here as you go from root S of 1735 up to 2195. There's certain regions where they appear to be mirror reflections of each other. And basically that's telling you something about the production mechanism here. And then these are the smaller elements, and in Volker, what Volker showed, it was almost impossible to distinguish them from 0. Here you can see some of them are definitely non-zero. Scales here go from 0 to 0.3 or so, up to 1 on the other plot. So that's the sort of thing. You bin these in bins of root S, and then there are angular distributions in the omega center of mass. So sort of summarizing, these spin density matrix elements, they're basically spin observables in the experiment that can connect to something we may be more familiar with, but they can also connect with theory on the production mechanisms. And I think Vincent will tell us some more about this later this afternoon. You can measure these for vector mesons, so we have rhos, omega, and phis. And measuring all of these will tell us something about the production mechanism, and basically these haven't measured very well here or not at all, so doing this for the first time is important. And as Volker mentioned, these will pin down amplitudes that are projected back to lower energy, so they're important for constraining things at lower energy. And these spin density matrix elements can be defined for any non-zero meson. So you could talk about them for spin 2 as well. They're observables. And I haven't thought real hard about measuring them for, say, the F2, which we've got a lot of, but in principle they're there, and they would tell us something about the production mechanism. So I'll just finish. This was a few references, and where a lot of this stuff came from. So I'll stop there.
All right, thank you very much, Curtis. You guys have questions for Curtis?
It's unfortunately very mathematical, and it's kind of a strange language to talk about it, but it's just another observable. It's what you've got to think of it as, and it really connects back to the things we're maybe more familiar with, like polarizations or something.
Yeah, sorry, can you explain that the tensor polarization again, please?
So it's basically it's the off-diagonal elements of the polarization. It's because the vector is the usual thing you'd think of as the three states, but there's can be correlations between them. So that's the tensor polarization comes there, and I actually recommend one of these other, like the Tabakin reference here or something where that's worked out. You can write them in terms of spin operators, and because you've got spin 1 There's just, you have to cross terms as well.
You guys have any more questions? All right, thank you, Curtis. It's not something that's talked about too often. It's nice to see everything, everything explained.
Agreed. Or confused. I'm not sure which I did.
No, that was great. And the references at the end are useful. All right, that concludes the session. We break for lunch, and we come back at 1:30.
Yeah.